All right. Well, thank you for the invitation for this machine learning and STEM summer school, week long, I think, right? Entire week long course. So I'm Kevin Roccapriore. I am founder and CEO of AtomQ. And so I was basically postdoc and then staff at Oak Ridge. And so maybe like an unconventional route to take to do kind of a commercialization of some of the technology that I was doing at the lab, and so on. So it's kind of an interesting route to take that I don't think is very like well advertised. And it's actually really cool that you can do something like this. And I had always wondered, doing some sort of research, even in the PhD, it's like, what's going to happen with this research? Is anyone going to do anything with it? And it's like, surely somebody does that, right? And maybe there is somewhat down the line, maybe 10, 20 years, but who better to do that than you who know it so well? So that was kind of the logic here. That being said, also, that's a big jump to take, a lot of risk. But this is why this Innovation Crossroads program was very useful in kind of de-risking, like personal risk anyways. And so they give you a stipend and such. So very, very good program. I can't talk well enough about it. So to get started with this talk, I'll be generally talking about atom manipulation, kind of a trajectory on how I started with it and kind of, and where I'm going and so on. And so I'm calling this deterministic atomic manufacturing. And deterministic is an important word in there, and it's used in the literature often also. So it's kind of difficult to separate what does that really mean and so on. But hopefully I'll get you to that point and what in terms of what I mean. And as per the request of Sergey, Thorfinn is my pet lizard, also is very important in this work. And so he needed to make an appearance, not in person though. So anyways, that's the only one. We'll see. All right. So motivations, like why do we, the STEM, I'll back up 1 second. STEM is used, it's a microscope, right? It's used for imaging, spectroscopy, analysis. But there's also another use, and that's this atomic manipulation or engineering. Not really what it was designed for, but it can be done in that way. And so why would we even want to do that? I mean, besides it being like the ultimate building block, essentially. So there are a couple big ones, and I'll split this into kind of quantum and semiconductor. And the quantum industry, there's many different ways to build quantum devices, computers, and so on. So this is kind of my vision, and not just my vision, but many people who are trying in this direction view this as a platform to, if you can build at the atomic scale, atom by atom, or even multiple atoms by atoms, you put them where you want them. You can now start to build some sort of useful quantum device, and you might be able to consider these as kind of qubits, and so on. And so why does that fit in the quantum world? Well, if anyone's familiar with the space, it's kind of there's lots and lots of hype and not a lot of progress, and there are multiple orders of magnitude really away from kind of like being quantum relevant for these like quantum computer type things. And so there's always these projections on when that's going to happen, but all of the technology is really progressing slowly, if at all. And so my idea has been to use a different kind of like modality to achieve this sort of thing. And so if we could manipulate these atoms in a controllable and scalable way, maybe we can actually break through and kind of jump orders of magnitude for the quantum world. And the semiconductor industry, a little bit easier to understand. I mean, Moore's law, you're just continuing to decrease in node size. And I will mention when it may not be clear, but when people mention, we're at the 3 nanometer node in the semiconductor, technology node, that's not actually 3 nanometers. It used to mean that. It doesn't mean it anymore. And it's a marketing scheme. So when they say 3 nanometers, it's something like actually 10 or 20 nanometers or something like this. So they're still far, far away, but still the point is, eventually they're approaching the level of building with atoms, and you can't do that with lithography anymore. You need a different technology, and so that's where this or potentially other schemes can come in. So there's a couple different ways, and I'll highlight a couple of them here. There's electron beams, ion beams, physical tips. The physical tips actually is from the 90s in a scanning probe. And they've been doing well on that. That's difficult though. It's a surface and it's very slow. So there are a lot of limitations there, but there's still ongoing work and a lot of funding for it too, I should say. Ion beams, I'm kind of going in backwards here, can be done in the same way. It's a bit more, bulky probe or tool here. So it's a lot of damage, not very deterministic. You're kind of blasting things, craters into things and seeing what sticks and which ones you like. And then electron beams in principle have the ability to do it. I mean, you can see the atoms very well, and maybe you can figure out a way to control where they go. So that's the idea there. So in the STEM, how has this kind of trajectory looked like so far? It was pretty early where people realized that you could actually move atoms with the electron beam. Most of the time, that's not desirable. You don't want to, modify what you're trying to inspect. So, you notice you take one image, you take another image, and atoms moved around, and you keep doing that. I mean, I have Batson from 2008. I think this is still much earlier than that even. But, around the time where you could really have aberration correctors and see this, that sort of thing, you could tell they started to move. And that's just in the TEM, I believe. And so not even with a focused probe. Shortly, maybe a decade later, Oak Ridge and another group of folks at Vienna and Austria have both demonstrated kind of what was apparently thought of as like kind of a model system, which is graphene, a single layer of carbon, pretty simple, and then a single dopant atom. And can you just move? Let's just start with one. In this case, I believe it's silicon in both of them. And can we, take an image, look where we are, and then grab the beam with the mouse and kind of move it around. And yes, you can. I think it's about, on average, at these currents, at the beam currents, it's about 10 seconds to move one atom, one location. So scaling that is very challenging, but in principle, the recipe is there. It's just a matter of figuring out how to do it. And so then this started to morph, and this is a little bit of where I started to look at this in more detail, is kind of, so by doing it by hand, you're using the mouse, and how do you even know where to put the probe to do something that you want to achieve? And so this is where, and I'll get to like an improved version of this, but we kind of need a data. I mean, there's theory that can be done here, but ultimately like a data-driven approach to kind of like, okay, you put the probe here, what happens? You put the probe there, what happens? And you just collect this thousands of data sets to kind of figure out which scenario is the most ideal to move that dopant atom from point A to point B, which is in this case just one lattice site. And so it looks like, okay, it is in fact directly on that neighbor carbon atom in this case. And I'll get into that in more detail later. But anyway, the point is that was kind of, we had to figure that out. And then, which in fact, it's funny, I did this before that, start to kind of build few atom structures with that. And again, it's slow. In that bottom right one, it's actually carbon vacancies, and it doesn't look great, but it is kind of an interesting approach. So we'll get into that. But all of this is kind of trending from manual operation into like machine learning and automation and so on. So it's like, scaling this is quite tricky. And so the usual workflow, which is where I started with this, is, you acquire an image. Maybe that's probably going to be noisy. In this case, it's a picture of graphene. And so if you have a better scattering material, you don't have to take as much time, but the idea is you don't want to spend that much time when you take the image because the probe and your manipulation tool are the same thing. So generally that's going to be noisy data, or maybe a sparse scan, for instance, and you want to get as much information as you can with the least amount of, electron dose in order to know. And the point is, where are the atoms so that you know where to put the beam? And so that's where these neural networks come in, and they can be pre-trained, they can be trained on the fly, some kind of like hybrid method that will work there. And then even after, training on them, defects will form, for instance, in here, and then you can classify the defects and other structures by like nearest neighbors or distances, and there's many different metrics that can be used there. And then you come up with some kind of scheme. You know where everything is. Now what do you do with that information? And that's kind of, and you also have some degree of a feedback. So one of the detectors or a camera can kind of tell you what else to do. So I'll start with this. I'll kind of try to go through these parts a bit quickly. So the idea here is you kind of take these frame by frame sequences. So you take one image, you find out where all of the atoms are, and then you start to do in this case, I call it avoidance patterning. And so you're not directly targeting any atom, you're just targeting you're drawing out a shape very similar to like e-beam lithography, but directly into a material. And then you want to see what happened. Did the carbon vacancy in this case, did it form or not? It's very difficult to know if it formed in real time because it's weakly scattering. So the idea is, okay, let's take a picture to see what it looks like. And so, okay, that's what it looks like in frame number 2. Not great. We're starting to form that hexagon. So where we formed it already, let's avoid putting the beam there again, but trace out that same path again. And so you keep doing that step by step, and kind of that was the idea. And you obviously, like, probably should stop at the third one, but what happens if you keep going? And so that's kind of the idea there. So it works not really well, but it sort of works. It's very difficult to do that, especially every time you take another image, you're also imparting some amount of dose in there, and things can change. And then we can also do this in other TMDs. In this case, this is actual atom targeting. So we, again, find where all of the atoms are, come up with some kind of strategy in advance on what we want to do with that information. And in this case, this is MOS2. So we want to target the sulfur, like diatom column, and knock out one of them, just one, not two. And the ability is there actually to do that. We can watch the detector feedback in real time and watch when we have a step profile. Suddenly, if you have 2 steps, then you can tell that that's actually 2 atoms. So you know where to stop, actually. So kind of interesting. So all of that was done in Python, kind of, come up with, you tell this, there's a lot of API access now to these systems. And so you can tell it to grab an image. You can have like a GPU or edge device that can decode or classify all of this, classify your image. And then you have this other strategy that can, position probe here and wait until, something happens, or just wait. And you can build different structures like that. Again, not super deterministic. It's difficult. I mean, I have a pretty example here. It doesn't work 100% of the time, and it's quite difficult. But Matt Bobinger and Ray Unisik, well, Matt is at Oak Ridge now. Ray is at North Carolina. They're a lot into these and other Maxine type device material systems, and so they're really pushing this pretty hard. There's other structures that you can build in MOS2 as well, or other TMDs. These are kind of sulfur vacancy lines. Instead of like knocking out, well, actually, if you knock out a line of sulfurs in a lateral plane, you can start to generate kind of other structures. And so the motivation here was, MOS2 is some semiconductor. Can you draw out a metallic line, for instance, and the conductivity of that strip can depend on how thick that sulfur vacancy line is. So that was kind of an interesting thought here. Can we do that? Can we draw patterns in conductive patterns in a semiconductor? And so maybe a little bit, these are only a couple of nanometers. And so always in the back of my mind is, how do you connect this to a device or make something out of it in the future? Of course, you have to do that while you're at whatever institution you're at. And so this is the other one I mentioned earlier about this like beam placement. How do you know where to put the beam to do something, right? And so this is this data-driven approach where, again, I kind of already mentioned a lot of this stuff here. So we place the beam. So here, you have a starting position on, you actually get this laser. No, that's not the laser pointer option. So you have a start image. And okay, clearly it's not very difficult to find where the dopant atom is if it's brighter. You don't even really need any fancy machine learning. And in fact, for a lot of this, determining these kind of beam placement rules or atomic manipulation rules, you don't actually really need any fancy, you don't need any neural networks or anything. You just need to know because you want some distribution anyway. So basically, you want a random distribution around that dopant atom relative to where you put your beam. And you just want an outcome of what happens. And so all that looks like is you put the beam somewhere around the dopant, and then, for some amount of time, you can control based on dwell time or a beam trajectory. Is it point in space? Is it fixed in time or not? It's easier to, there's a large space actually. So to keep it simple, in this case, it's just a point dwell, I believe for 5 or 10 seconds. I can't remember which. And you record a small image, not this large of an image, but a small subscan of kind of what happened. Did it move? Did it not move? And so on. So you just keep doing that over and over again, and you come up with some contour kind of plot on the right. And, that's not the actual one, I think. Yeah, it's like, is it maybe on the bond between the two? Like, is it clear where we should put the beam? I mean, people thought you put it on the neighbor atom, the neighbor carbon, and it turned out to be right. So this isn't a big surprise, but it would have been cool if it wasn't there. But in any case, the agent actually learned that on its own. We didn't inject any physics into that, and so it kind of figured that out. And so with that knowledge, you can then start to automate the process, walk the silicon or whatever dopant atom around throughout the lattice, wherever you want. And then you can start to build, you bring one silicon and you bring another one, and you can, think of building structures that way. In practice, it turns out to be tricky because every time you try moving a second or third one to the first one might move. And so it starts to get more and more complicated. And I should mention here, what I showed was, so for each of these are just a couple of different configurations, but for each of them, the rules or kind of like rates of motion, displacement rate might be different for the different configurations. Maybe you don't want to put it on the carbon atom neighbor when it's in a fourfold configuration. It turns out fourfold is much more stable and harder to move, actually. And then, of course, when you get even more defects, what happens? So this can be starting to get to a very complicated problem. Obviously, you'd want to stick with the most simple case so you can kind of, make it simple. But turns out that sometimes these defects will just form without you wanting them to. And so, that's kind of what it looks like. So this kind of, automated, autonomously did it. And so one of the interesting things is here, what is the path to take? And so in this case, I didn't come up with the path. I just said, where should the final position be? And that's it. And then, maybe you can jump more than one atomic site with one beam placement. So there's starts to get like different sort of rules and different sort of strategies for manipulating these single atoms around that you may not have even thought of. And so that's kind of where this all came in, and this just kind of moved it a couple, I don't know, 5 or 6 lattice sites or something in total. But it did it on its own based on the rules that it learned from all of this kind of like deep neural nets and just lots of data. So that's nice thing about having a lot of data is you can do that. And it's not a tremendous amount of data like some of these, billion parameter models or anything. You really only need like a couple of days worth once you figure out how to do it, a couple of days worth of data or something, maybe not even. And that might already be enough. So that's like this big data challenge, really don't need big data for a lot of this. And I think that's one of Sergey's points is small data can work too, especially when it's kind of domain specific. So generally, all that, what I'm trying to say is what we found out was, yes, the beam can move the atoms around, but what I've showed so far is really just only a few atoms. What I didn't mention is if you take it out of the microscope, what do you think happens to it? Nothing good usually. So if it's a single layer of carbon and there's carbon in the air, then you can imagine that all of your efforts are just gone. And so there are other ways to maybe get around that by encapsulating it before you do that, or even in the system if you can do that. But generally, it's very difficult to make use of these things inside that environment. And then, of course, it's cool to move them around, but is there a reason to do that? Do they have a property? So there's a lot of theory behind that, and remains to be really seen what can be done. And so let's see, there are a couple more images. I can mention, yes, the cloud of contamination just gets all over your stuff. And one of the things that I would say that kind of put a roadblock in a lot of this stuff is the fact that you're taking an image each time that you want to know where all of the atoms are. And every time you do that, something changes. Number one. And number two, the image that you take may not actually be where the atoms are when you want to go and place the probe there. And that's due to not only something like time factor, like, okay, you take the image, maybe it's drifting, and you put the beam where you thought it was and it's moved. Sure, that can happen. It's also from scan distortion. So even kind of a simple, usual raster scan will already distort. And so you can see that just by slowing up or speeding down your scan rate or dwell time in a regular microscope, and you'll just see the image shift in either direction, in the fast scan direction. And so those kind of together, turns out that when you try to position the beam relative to an image, it's actually not even what you think it is. So that's kind of the next segment of the talk is going into, can we do something about that, basically? And in order to do it, it wasn't immediately available to kind of come up with a custom scan. So you can program scans somewhat, I think, depending on a hardware controller that you have. You can kind of do some of the things in Python. They're a little slow, and it motivated me to build my own controller in order to just do a custom trajectory of the beam, because that's what I wanted to do. I wanted to minimize those distortions and kind of do some other things. And so that's what this is for. There are other things on the market that can do that. I think Gatan has one, although it's very expensive. And then the other kind of big development is pushing that precision of the placement of the beam be less than 20 picometers and non-invasively. So this is kind of it didn't originally make sense to me. What does that even mean? Because, we hear some of these academic papers say, oh, we measured these like few picometer level distortions from these images. And so clearly we have the information that is like few picometer when we get a regular image. But the point isn't that. The point is, can you put the beam directly on an atom core within 10 picometers of where it actually is? And so it's not as simple as saying, I have the image, let me just put the beam right on that atom and I'm done. It turns out that it's off quite a lot, even like a unit cell sometimes. And so that turns out to be a big issue. And also, how can you get that level of precision without dosing and dumping a whole ton of electrons all over the place? So it turns out to be a little challenging. And I'll go into that in a minute. And then again, what do you do with that information? And this is likely material dependent and really needs to be explored a lot more. But you need some kind of like strategy on what you do with that beam. Is it fixed in time? Is it moving in time? Are you doing something based on a feedback, and so on? And so, for instance, in one of these images, let's say the beam does some kind of traces out a figure eight over there. Okay, it does that. Okay, what if we do it in the other direction? Does something else happen? Okay, so we move them in different directions based on a little bit of a different scan. And again, I'll get into that as well. So the point is there's lots of degrees of freedom here to explore. And again, how important is precision and how much do we actually need in terms, and again, I mean placement precision of the beam. And so kind of a really neat study, a neat experiment that was carried out recently in this chromium sulfur bromide case is it came out from the reviewer too, number two. He's always got to watch out for this guy, but in this case, it turned out to be a good question and really helpful. And so in any case, what we did here was, this is a unit cell of this particular view that we're doing the manipulation of. And again, it's very similar to what I had shown in this silicon or the dopant in graphene, but I have like it's a little bit better of a picture of what happens when you do that. And so there's something like 5,000 or 6,000 different sites that you randomly do. And again, don't need any machine learning or anything for this. And because the crystal is periodic, you just place the beam anywhere you want, literally just every couple of nanometers, place the beam somewhere. And then you can collect all of those results. And then by the Wigner-Weitzel kind of collect all that together in composite like format. And so it turns out, okay, in this case, so you can kind of make a mosaic of what happens, like what's the resulting effect at each of these different positions. And I kind of bin these into like discrete patches here. But if you can see, okay, if we put the beam like in this green guy over here, which is basically somewhere over here on the right-hand side of the unit cell, it turns out that when we do that particular scan, this column gets brighter. Both columns get bright, but this right-hand side gets brighter. If we put it right in the middle of that unit cell, both columns basically get equally bright on the left and the right. And then same for like the left side. The left one gets bright. If we put it all the way at the top, kind of like the topmost one is most bright, the other one. So anyway, the point is you can kind of start to extract what happens, not just to, in this case, not just to one atom column, but to 9 different columns based on your one beam position. And in this case, it's kind of a line scan. That's what the arrows going left and right are. So there's kind of these things that you can pull out now, and then you can kind of build out like, okay, each column based on the position. So this bottom left map is based on the position of the beam, like the center, the centroid, what happens to each of those 9 columns. And so you can see like some of these guys, like this column loses atoms, this one gains atoms. So actually in this particular case, and I'll show the structure of this in a minute, the center column atom moves either to the left or the right or to the up or the down. And sometimes these other corner columns, which are, they're all chrome or chromium, end up losing atoms, losing their atoms too if you're too close to that. And so it turns out that you do want your probe very precisely positioned, and from all of that, extracting it, turns out you need something like 10 or 15, 20 picometer precision almost. So that's not so easy to do, but maybe we can get there. So that's the idea. Okay, 5,700 positions, and you can find out all these different, what happens to each column at all the different sites. And so usually you don't want something happening to all these other columns. That's the point. And so you only want something happening to, like, for instance, just that center column and maybe just the ones to the left, or just the ones to the left, or both left and right. So how do you achieve that? Well, you need that much position confidence in positioning. And so that's difficult to achieve. And so we're saying less than 20 picometers to kind of have a deterministic outcome. And so, you want the atoms to move where you want. And then sometimes you don't want some other guy to pop over here and ruin some, collective behavior that you're trying to achieve. So that turns out to be tricky. And so this is where I get into, well, how do you actually do it? And like I mentioned, traditionally, you take an image and then you can do it by hand, more sophisticated, or quickly you do it by machine learning or neural networks or log methods. There's many different ways to extract that information from an image. And then, you put that beam relative to that image. But again, there's distortions and there's other reasons I'll get to in a minute. But turns out like this is the horizontal distortion and even some vertical distortion. These scan coils are not perfect by any means. The day we have electrostatic scan coils, I think we'll be much happier in a better place. But until then, that kind of scan, the raster scan, is not going to work so well. And of course, drift in time. How good is your stage? How long ago did you move it? Is there a train nearby? Obviously, there's a lot of problems with this, even temperature fluctuations. So you've got to keep track of things very, very well to do this. And of course, the other things, every time you image it, it'll start to transform. Maybe you want that to happen, but maybe not. So there's many issues here. So again, these linear distortions, these are well known, flyback distortion. It's not so difficult to overcome this with a, constant velocity scan. So spirals are a good candidate for that. And so that's kind of what we did here. And so Not actually a full spiral though, if you notice. And so it's just an annulus. So it's a ring. And so the idea is your target is somewhere in the middle of that ring. You don't know exactly where, but you end up sweeping around it and taking the assumption that you have a periodic crystal. You know the orientation of that ahead of time. But if you know that crystal structure and you can pick out, the specific bright spots that correspond to atoms, then you can kind of reconstruct what that information is. Where's the lattice? And you do it without ever actually hitting in that center area. And you're doing it with a very, it's already a sparse scan, but you're never hitting that center area. So this is what, I guess nothing else to mention here. So that looks something like this. So this image is taken just to show you what it looks like. And that's the typical radius of the spiral or the annulus. And so what does it look like? So, you can, based on, there's a number of parameters for this, which is another thing to figure out for that are material dependent, orientation dependent, voltage dependent, maybe even. But the idea is you want a couple of loops to hit the same column multiple times, so you have a good confidence that there is an atom there. It's not just a bright pixel from noise. And so that's what's happening in that first case is, two of those scan loops hit that one atom, so with high confidence that there's a bright column there. And so you do that for all of them, and you can then reconstruct basically. You kind of filter it, you can threshold these things. There's a number of different ways to do it, but you have the matched ideal lattice, and then you can do a minimization, and then you know where everything is. And so it's just a translation, really. And so this is what we've called as atomic lock-on. And so you can get better than 20 picometer precision in doing that. The scan itself can take, it's dependent on material, but in this case, it's like 50 or 100 milliseconds of a scan. And what was the computation time? Like 20 or 30 milliseconds, I think, something like that. So it's pretty quick, and you can know exactly where you want to target without ever hitting it. So it's kind of a blind version of hitting an atom which has never received dose. And then the radius of that can be smaller or larger. There's a lot of different parameters to vary, and so on. So that was fun. So this is one of these good visual representations of what happens when you don't have it. So this is what I started with on the left, just trying to target that center atom, which is the darker one, like hundreds of times or something like that. So you take an image, you predict all of the coordinates, and then you take a subscan centered at that coordinate that you want, and it almost looks just totally random. And then if you have the atomic lock on, then this is the point is, okay, you're much more confident in doing it. And so this was frustrating originally because, I know where the atoms are. Why isn't this working? So it turns out that it was a bit challenging. So anyways, so the precision, if you try looking at the precision, it's a unit cell. So you don't even know if the thing went further than a unit cell in this case. So it's worse than that, most likely. And so with that information, then you can start to target, not just the different atoms, but you can target the bonds very precisely and so on. And so maybe that's worth doing. Maybe it's not worth doing. It depends. You can track different dopant atoms this way. I'll try to go through this part quickly. You want to hit a dopant atom that might be beam sensitive, and you want to maybe get the eels out of it, or you want to see, what is its fine structure, or you want to see what does its transformation look like every time you hit it with, 100 electrons, what happens? And so you can kind of monitor different things like that in time that you can now do because you have that level of precision. Same thing with the eels. Does it change in time? That's when it was very difficult to tell if it changes in time. So that was challenging, but we did it a number of times. So I'll do that one. Some of the other ones, so this is relevant to kind of MOS2. When you have that sulfur dimer, you can see when this is the step profile I was talking about before. So you can actually see when one sulfur is ejected and when that second one is ejected. So that actually is very interesting. Not so surprising, but there are other interesting things. If you kind of clean up this data a bit, it looks like there's another little pop here, this little spike here. Does that correspond to something? And so it looks like in a couple of these scenarios, I don't think I have a good one here, but it's in this paper. Sometimes the sulfur is not actually ejected, it comes back. So they're kind of like dangling bond here. And so you can maybe even pull it back. And so there's a lot of interesting dynamics that can kind of start to be extracted from here that weren't so intuitive. Um, it's not fully ejected sometimes, or maybe there's another sulfur that can pop back in. Okay, the last few minutes, I want to take some time to go from this atomic engineering and manipulation to kind of like manufacturing. This is like the commercialization aspect of it. How do we make use of it? So this structure that I'm working with is about 10 or 20 layers thick. It's chromium sulfur bromide. And thick, it looks like way more complicated than you want to deal with, like graphene, much easier model system, but it turns out that has problems. So in this case, we end up manipulating an entire column of atoms, and we end up moving them from one column to another. So there's no, additional source of dopant, which actually that's a challenge right there. And there's no loss of material if you're careful enough. And so you can make use of kind of beam channeling if your positioning is good enough to not scatter the beam all over the place. And so that's the idea here. And so can we make some like artificial structure? And so the idea is something that's repeatable, deterministic, and it's reasonably fast that you can scale. And so that's the idea here. We do a couple of positioning algorithm and then a specific scan, kind of a horizontal scan to get these things kind of scaled up in a larger pattern. So that's still only like 10 nanometers or 12 nanometers, but that's kind of the building block here is that kind of defect structure, which is a kind of vacancy in the middle and then an interstitial, that chromium atom goes into the gap between the layers, and then it does that for all of the layers. And so that's what you're seeing here. And so those are, whatever, a couple of nanometers periodicity. You can vary those, get them as good as 2-unit cells. Closer than that is very challenging. And that was just published a month ago in Nature, finally, the first one I had, yay. And what else? Let's see. That's what I mentioned. Okay, vacancy interstitial pair. And those things are technically they can be quantum emitters in the telecom. So potentially we can couple these, they can start to couple, you can build these artificial crystals that talk to one another with inside of a crystal already. So there's a lot of motivation there. This is a schematic. And one of the interesting things is, I'll show this bigger picture here. Based on the beam direction that you scan, given the knowledge of where you are, you can get different outcomes. And so you can move these atoms in different columns to give a different configuration, different optical properties, different electronic structure entirely. So you have a large degree of freedom with just that. And that's just this one material system. Really needs to be explored on a lot of other things. And I'll mention, so you can obviously do other shapes as well, spirals, stars, the North Star, Lie lattice, and so on. You can do alternating patterns. Of course, company logos, that's very important. What else can we do? You can order a logo today. No, I'm kidding. And then one of the last things I'll mention is the stability. And so it's actually from the review in this paper, one of the questions was, well, it's odd that it's even thermodynamically stable in the microscope, but surely outside of the microscope, it's not. And so that's a good question. And so that was something we hadn't even looked at until the review. So finally, a review that worked. It turns out that calculation-wise, they have a pretty decent, barrier to go back into their original state. So they can sit right in, depending on which defect structure you make, they have a decent amount of energy to overcome in order to get out of that one. So they are definitely thermodynamically stable, but are they air stable? And it turns out, so in the before picture here, we did this, he took it out of the microscope, set it on the desk for an hour in air, and then put it back in and found them again. Finding them is non-trivial, but we did. And the same defect structure is there. And so I'll put them side by side. And it looks like they're still there, they're stable. And the fact is that this is a layered structure. Maybe the surfaces aren't so great. Well, we don't really know, but internally, all of that is mostly still the same. And just for kicks, if you take another image, suddenly the second frame and the third frame really starts to deteriorate. And so this is just to emphasize how much the imaging really affects things, at least in this particular crystal. So that's pretty good news for integrating it into a device. And I'll wrap up here in a second. And so we wanted to see how far we could push this. And we did this this is not the full image. You can't really see the full image, but this is it's 100 by 100 by 150 nanometers array of about 40,000 of these. That's including the depth of these structures. So we were able to do about 40,000. So it's like on the order of 100 nanometers, almost, one order of magnitude, and we're micro machining now. And so, when we did it in the different orientation, so different orientation gives different property, and not only that, but the distance between defects. Now you're making an artificial lattice, so the periodicity also changes what the properties you have. So again, lots of degrees of freedom, but the aim is to get to micron scale so that we have the ability to use these optically, for instance. And then the last thing is, one of the really neat things was electron diffraction. So in kind of nano beam mode, like a milliradian semi-convergence angle, looking at this pristine material, okay, you have that here. And it turns out, okay, when we look at exactly these two structures in diffraction, you do see the superlattice structures, which is beautiful. And it really confirms that it's not some weird imaging artifact. It's really there. So that was pretty cool to see that. And then this is the last slide, just to show what does that spacing do when you make an artificial lattice. So you basically Hamiltonian engineering things. You're really just changing the energy landscape, and that can enter into different regimes of like superconductivity, Mott-Insulator, depending on what you do. So this needs to be explored experimentally. There's a lot of theory behind it, but we're excited to build that and test them. I guess that's just going through it. And I think that's kind of it. So this collective state engineering is kind of what I'm after here. And with that, thank you for your attention. And that's it. You don't know when this ends. Yeah.
A lot of questions.
I can't see them. Where are they? Oh, wait. I got to get back to my mouse. Okay, here we go.
Huh. No, go to your...
Where's the Zoom?
No.
Well, I guess I can just stop share or stop presenting.
No, just to...
Escape? Wait, go back here. Click escape.
No.
Oh, wait, chat. I see it down here now. I forgot I hid that thing. Okay. Residual aberrations.
You have a lot of them before that, I think, as well. No? Oh, yeah. So you have residual. You have lots. Yeah. You have a lot of stuff.
Okay, yeah. Aberrations. Yes. That's a... Yeah. I'll start with this one. Just looked at it. So yeah, aberrations are incredibly important here, and maintaining them in time is also very important. So those large arrays, just to give a perspective, the 100 nanometer one, that takes about an hour to do. I want to get that divided. I want that time cut in half or more. But an hour of maintaining focus, for one, most important, but astigmatism and coma are actually very important too. I mean, luckily for the neon system anyway, the aberration, and I think this is true for most systems, the higher order ones are fairly stable. But they still do need to be checked quite frequently and corrected. And there are kind of schemes on how to do that without like the traditional, can you do it with the information that is already being obtained when you're doing all of these manipulation events? And that's kind of one of the to-do items here. But yeah, it actually turns out to be, your beam needs to be very, very good. I wouldn't say number one thing. I think still the positioning is the ultra critical piece there that wasn't so clear, and that one is very important. But yeah, everything's important, I guess. But anyways, but yeah, okay. Adding a degree of freedom though, that's a good question. The depth of focus or the changing defocus, that's something I do want to explore. I don't know how much control in the lateral or the Z direction, the beam direction will have, but it's something to look at. But good question. I saw you first.
I wonder if you try working with this approach with really hard materials like diamonds?
Diamond, no, it's a good question. In fact, because the vacancies in diamond structure is in the back of my head. I haven't tried it, but one thing I'm skeptical, not skeptical, but just anything with carbon is very frustrating to work with, particularly graphene. But it's not that it's not possible, but yeah, I don't know. The carbon, it feels like there's just carbon everywhere, and dealing with carbon is already challenging. And so weakly scattering, and maybe it's very thick, different story, but I don't know. I haven't tried it. So it's something on the list, though. Well, good question. I'll just go for you real quick. Yeah.
I have a couple questions. One of them you answered earlier.
Good.
So like, one question is, how do you know the chromium atom force between the layers?
How do you know the chromium, what between them?
The atom, after you knock it out.
How do you know it's moved?
How do you know it's where it is? It's
Yes.
between layers, because I remember on slide 29, you said
Yes.
falling into the layers.
Yeah, okay, sure. So yeah, the question is, how do you know kind of if you've moved the chromium atom into the right place? Is that effectively kind of the question? So I guess I can go back. You said 29, right? Let's go quickly. Too many animations, sorry. And here. Is there a picture of it maybe? Here. Here. Yes. Well, you don't know which chromium and which layer you're manipulating, but what you do know is when one migrates into the neighbor column. So in this case, I didn't mention it. Well, I sort of mentioned it, but not really. So in this case, the beam action, so like you can call it the beam trajectory as a function of x, y, and time, is something that kind of like sweeps back and forth. So you're probing all three columns at the same time quickly. And so you can start to see, okay, you're watching one column, you can kind of like break that scan out in like a live view, and you can watch one column start to go down, which is the middle one, and the other two columns go up. And then you can start to see it's debatable if you can actually see those as steps, as individual atoms. They usually seem to go in like clusters, but quantifying like single atoms, very difficult there. But the point is, while you are doing this manipulation event, you're you're always getting data from your annular dark field detector, and don't throw that away. Use it is the idea here. So that's how that's done.
So my second question, I think you touched on it earlier a little bit. The focused scan is a very, you can think of the probe is very small. So when you actually have this multi-layer system, how do you know you changed what's the column in the whole thing?
And that's a very good question. Yeah, so short answer is beam channeling. So there's simulations, I didn't include them here, but if your probe is focused probe, you'd imagine it just defocuses throughout and just hits everything. If that does happen, if you are not on a column, but if you're directly on the column, it channels the nuclear forces. I'm not actually sure what's responsible for the channeling, but when you're on a column, it constricts the beam waist and kind of like guides it through. And so it does not scatter, and it stays very finely tight-waisted and goes all the way through. But that's another reason for having that precision. If you lose that precision off a little bit, now suddenly you're spraying those electrons everywhere. So yeah, that's a good practical question. So yeah, I appreciate that. I'll go back to the chat. Oh, Shantanu. Okay, after moving one atom from a position, the energy barrier for the second atom, do you change the energetics? I don't know. Short answer. It does feel like it cascades quicker. the further you go, or I don't know. It turns out that the very beginning of the process is very important. So those like first like 20 milliseconds, you might be able to get a big chunk of atoms moved out, maybe like a third of them or something. So each, to give another perspective, each site that you're at, if there's 20 layers, I'm spending about 1 second or half a second to get all 20 layers moved, or majority of them. We actually don't know for sure if all of them have moved. That's a difficult one too. But yeah, that one, it does seem like it's nonlinear in terms of, do these, I mean, in this system, they are that each layer is very decoupled from the next, but it does still seem like empirically that it is a little different. Like each atom goes faster than the last, for instance. Not too sure about that one. Anyway, next question. Anyone else? Yes.
So I have a very basic so when you start application to imaging mode, do you like just play with build time or like the big current?
Well, there is, in this case, the only reason you're seeing an image is because there was a paper. So in practical scenario, I would never image. I would always be in this fabrication mode, and I would be getting the information that I need to do the fabrication in that same mode. So there is only one mode. It's non-trivial to do that, but that's the idea, is you just don't want, I mean, you need to get the aberrations corrected and all that kind of beforehand. You need to know the orientation of your crystal. Okay, there's certain things you need to know, but then you push that aside and you're only in fabrication mode for the rest of the time. And if you want to take a picture of things afterwards, okay. And that's the idea. Just by taking this picture, this image, I've already changed it, So it looked better than that before. Be rest assured. So yeah, that's the idea.
I have a quick question. So, you try working with lanthanide point defects? I mean, remove lanthanide.
Me? No, I've not touched on any of those. Have I? No, I haven't touched any of those. So I mean, that's the thing. Like, now that this tool effectively exists in terms of positioning and like algorithms kind of, and all the machine learning, even, like there's so many systems that need to be explored. Like what happens, I don't know if this is the ideal system or not. This chromium sulfur bromide seems to work well, but there's a class of those. There's other things that should be, I should revisit even like the dopant and graphene thing. I didn't have this positioning algorithm and so on before. I don't want to work with graphene, but yeah, the point is still like lots to explore, and I don't even have that much time to do all that. So yes, it certainly needs to be looked at. I can at least respond here.